Okay, so in series, as we add resistors, resistance total goes up. But I said this 100 times, I'll say it 101. Please never base your arguments based on resistance. Resistance doesn't actually go up. It's a mathematical ratio of voltage and current. So what actually happens is the next relationships that then in turn affect current. And that is, what does voltage do?
Decrease. Well, you add them together. Stays the same.
The total voltage coming out of the battery stays the same, and voltage splits is what we're looking at between both resistors. Meaning, the way you could look at voltage is, if this is, say, 12 volts, this would be 8 volts, and this would be 4, for just making something up real quick. Now, obviously, that would be set by the resistance, something to the effect of, let's go, this is 200 ohms, and this is 100 ohms in this particular case. Now, how do I look at voltage? Well, there's voltage gain and there is voltage loss. As you look at a relationship such as this, there's one voltage gain caused by this particular battery, and there's 2 voltage losses. Now, if you want to use any one of my analogies, I'll begin with the first one. The first analogy is it's like 2 slides being stacked on top of each other, and the battery is like a ladder. You only get so much energy of the hill. So the interesting thing about this split is it feels like from this relationship that you are adding voltage. You are not adding voltage. You are literally splitting up the voltage that is available. Yes? Another analogy that you could use, that I've used, is kind of basically like voltage is the amount of joules per coulomb, or you could look at a charge being like an energy carrier, that each 1 coulomb gets 12 joules, or each child gets 12 jelly beans. And as the child tries to get through the hallway, if they pass by bullies, okay, if they pass by bullies, you're going to need twice as many jelly beans to get by this one. In this particular case, you only have ever 12 jelly beans specifically to go through. Now, the question then becomes, how does the child know? Well, ultimately, and this is a little bit where my analogy breaks down, there's trillions upon trillions upon trillions of jelly beans all attempting to go through this particular system at the exact same time. And these very quickly get up into equilibrium, right? So they're trying to, this is a constant rate. So you can kind of think about it like, how do these jelly beans know they're going to need, or these charges know they need to spend more because somebody passed back the information, blah, 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 that there's, yeah, so it just splits how much energy it takes to go through that. Yes?
Okay, so when I was doing the homework, I ran into a problem because I know it's like when the voltage splits, like you can only have that certain amount of voltage for that path. Mm-hmm. And so when the voltage splits, you said it was a ratio game, and so I understood that, but I didn't understand.
Well, voltage wouldn't be, current would be.
But I didn't understand how the voltage would split. Like,
let's get to that. Let's get that in this particular case. Okay. If you get up into systems that are more complicated than straight series and straight parallel, you kind of have to use a combination of those particular factors. And so let's go through these rules, and then we will tackle any particular questions that come up. Okay. So voltage is going to split. What is current going to do?
Current will
be the same throughout. What this equation says, this says that the total voltage or total energy applied by that battery is going to have the split between each resistor, 1, 2, 3, and so on for however many particular resistors there are. So there's only 2 resistors here, so it'll only be split twice. This says that the total current leaving this particular spot, okay, is going to be the same as the current in there is going to be the same as the current in there. In my analogy with the kids going through the hallway, this would be tracking how many kids per second pass by this one. And imagine that you've got every single kid in Alton High and even in the surrounding area file into the hallway up here on the 3rd floor. Are you going to be able to move faster than the kids in front of you? And on top of that, maybe sure you do go fast, but if we look at the average number of kids that pass by a point, that would be essentially current. Now, why would current decrease? Well, current decreases because do you have as much energy to go through here? No. So since you don't have as much energy to go through there, what's going to inherently happen to your... If I had 12 volts on that, I'd have a certain current, right? If I have 4 volts, 3 times less the amount of voltage, what happens to my current? It should be 3 times less. AKA, this is actually what happens. Since the voltage splits, current decreases. And when you look at what resistance actually is, the ratio of voltage to current, as the current decreases, and this is, by the way, looking at the totals. The total voltage hasn't decreased, the individual ones did. If the total current decreases, decreases, then what's going to happen to resistance? That's why total resistance effectively increases in this particular case. And then we showed the math. Essentially, it was this, that resistance total, or AKA equivalent, is equal to resistance 1 plus resistance 2 plus resistance 3. And this is where I mention a very similar rule, but the opposite of that in capacitors, that you will definitely want moving forward, and it is simply this. The total resistance will always be bigger than any one of these individually, which makes sense, just mathematically. Everybody questions? Okay, when we last left our intrepid heroes, they were moving on to parallel. And I should begin with this. If I have a 120 volt outlet, and this resistor is 120 ohms, which we actually discussed is a pretty standard resistance for a battery. We can talk about that a little more in a second. How much current should be going through that battery? 1. Okay, this is like a ladder and a slide. This is a simple ladder slide combo right here, right? So we've got what gives the energy? The battery. What takes the energy away? Going down the hill. What happens to your total energy? It's conserved. So the voltage, so the energy gained is the energy lost. So if I gain 120, guess how much I'm going to lose here? 120. Now, when I add a second light bulb, okay, we've got a second slide, essentially, if you will. Same ladder. You still climb the same ladder, but now you could go down this slide right over here, right? Now, will that affect, keeping in mind that this ladder, okay, this is where analogy definitely breaks down. This ladder is like infinitely big. You can have as many kids freaking on that ladder as you possibly want, okay? Put as many, that's not a limiting reagent. So will that change how many kids can go down this slide? No, it doesn't. Meaning this will still get all the energy, still the same resistance, and so it still gets a current of 1 amp. Okay? If I have another 120 ohm resistor here, guess how much current it's going to get? 1 amp. And of course, I could do that time after time after time. I could have 6 paths. Is the 6th path going to change the first one in the slightest? No, which is good, because power is how much current and how much voltage is going past a particular resistor. And this battery, this light bulb here, has the exact same voltage that it did at the beginning, and is the exact same current that it did in the beginning. So will the light bulb still work exactly the same if you plug in a second, third, fourth, or fifth light bulb? Yes, which is great, except there is one thing that it is actually changing. It's not this path that's changing, it's this path that's changing. If I have to pull 2 amps, one down this path and one down this path, I'm switching to, I believe, my 3rd or 4th analogy on the day. Think of it like cars. This is 1 car per second. This is 1 car per second, adding another lane and another lane and another lane, 1 car per second. So what am I doing? I am pulling more total cars out of that guy right there. Currently, how many, pun intended, how many cars per second am I pulling in that wire? 2. Add another one. Doesn't change anything about these. And that's where it's interesting, because on the last one, what I said is that this relationship is not actually adding voltage. It's taking the current voltage and splitting up where it goes. Yes? Whereas, while the relationship looks identical, sorry, that's the force diagram of somebody in a car accident, with and without a seatbelt. You remember that. Okay? If I have this relationship, which looks like this, while the previous one was not actually adding any voltage but splitting it up, is this adding extra current? Yes, it is. It's the opposite. I want to say that again. So if you will, this is like having a giant ladder and one slide that leads to another slide. Can I ever have more voltage than this battery if I don't change the battery? No, I can only get 12. I can split it up further. If I put another resistor on here, let's say they're all the same. Let's go back to this and say they're all exactly the same. How much voltage are each of these resistors going to get? So 6. Now I add another one. Each one of them now have 4. Notice I'm not getting any more out of it. I'm just splitting it up further and further. Whereas the opposite is true here. Even though the relationship looks, positioning was on accident there, the same, it's not quite the same, because is this just taking the current and splitting it further and further and further? No. This is actually adding to the total current. What would the total current be if it looked like this? 1 amp. I add, oops, backwards the other way. I add 1 path. What's the total current now? 2. I add another path, assuming they're all the same resistance. What's the current total current now? Point being, I am actually adding total current, unlike splitting it up in the previous example. Does that make sense-ish?
How does it add current? How
So think of it like cars, okay? Think of it like cars, and these like a lane of traffic, right? I can only get 1 car per second down this lane of traffic. That's it. That's the max that I can do. So this current doesn't change. But if I add another resistor, I can fit now 1 more car down this. So how many total cars are coming down this lane? 2 cars per second.
Okay, I think I get it. I was just thinking where were the cars coming from, but I guess there's an infinite amount of cars. So the traffic the traffic is basically distributing, so then you can get more per second.
Yeah, and one thing to think about here that some people struggle with a little bit at the beginning of circuits is they go, oh, but this one's further. Okay, keep in mind, this is just how I have drawn it. I could also draw this exact same circuit like this. Right? It's just, there's another way to say it. Do wires actually have resistance?
Yeah.
At the relatively low distances that we use, and large gauge, aka area, basically all of the wires back there, even though they do have some resistance, it's basically 0. Or it's so close to 0 that we would assume wires have absolutely no limitation. So if you want to think about this in terms of traffic, think of wires as basically a 700 lane traffic, okay? Are you ever going to have any limitation because of that? No. Whereas resistors are now taking that 700 lanes and putting it down to 3 or down to 2. Now, is that going to limit it? Absolutely. Is there going to be a slower flow of traffic coming through these lanes now? 100%, even though they're wide open. Trent.
Why does energy come out at the resistor instead of along the wire? Like the light bulb lets out energy.
So 100%. Because it takes energy to go through. Is the energy spent is energy used. It's a work being done. So in other words, this kind of goes back to the Wimhurst machine. Why does light come out? Because energy is being pulled out of the electron. Why? Because there's electrons over here, negative. There's a positive over there, and what does the positive do to the negatives? Pulls them through the air. So is work being done on the electron? Yes, being pulled that way, and it's going that way. If that energy is being pulled out of the electron, it has to go in some particular form. That form, if we looked at nothing else, of course, you would assume would be kinetic. But kinetic energy from a bunch of different viewpoints is just temperature, sound, and light.
So it's harder to go through the resistor, so more energy.
Yeah. Yeah. And that's why I use my analogies of either the water slide one. This is where you get your energy out as you go down the water slide. Or my bully example. Why do I spend energy? Well, that's where I have to spend energy to get through the bully. Or in terms of my traffic example, you could say gas. Arguably, it's a little bit weird, but it takes arguably no gas to get anywhere in here because there's nothing. I'm just flying around by the seat of my pants. It takes all of my gas potentially to go through that particular area right there. Yes.
Okay, wait, hold on. So the light bulb lights up because there's energy being spent. But
yes.
If the energy's spent, then why is it going in a circle back to the battery?
So think of it. It's energy per charge. Energy per charge going through. So like each charge has its own energy, and also energy doesn't indicate that it's not moving. Okay, it just means that just like these are still moving. Look, it's like this. If let's say you had a chutes and ladders situation in which there was no one in your way, right? There was easy peasy day. You'd move, let's say, at a constant velocity through. Now, it's not quite perfect for this because obviously as you go down the slide, you're going to speed up. But let's assume you're going about the constant velocity. Does my velocity change? No. Therefore, does my kinetic energy change? No. It's not kinetic energy is the issue here. It's potential energy going out in the form of some other means, in the form of, in this case, light, and it's basically the molecules wiggling in there. They're wiggling hard to get through there. The only difference between a resistor and a light bulb is that light bulb have a clear path, so you can see the wiggling that's happening inside, specifically the filament. A light bulb is nothing more than a piece of metal. It's a filament. A filament is just a piece of metal, and what happens as that thing has more and more energy going through it? Vibrates, and we'll talk in the next coming chapters about what light is and therefore what that puts out. But for right now, there we go. All right, next thing I just wrote up there is voltage is the same. In terms of my analogies, hopefully that makes sense. I'll give you every analogy again. Here it is. One ladder, 3 different possible slides to go down. Okay. What confuses people when I said each of them get 120 volts, let's go ahead and actually use another color here. When I say each of them get 120 volts, they go, but Spainhour, you only have 120 volts. What do you mean? Why is that? Isn't that like 360? No, it's absolutely not, because volts are joule per coulomb. Yes? And if you think of the current as coulombs per second, you can kind of think of a coulomb, I know it's not quite this way, a coulomb as being like a person going down. Can this one coulomb, which carries with it 120 joules, because it is up on the platform, can it go down all 3 slides? No. If it goes down this slide, it's now at the ground. How much energy has it used? 120, unless it goes back to the ladder and get it again. Yes? And this one coulomb doesn't want to go down that slide, so it goes down this one. So it's also going to use 120. Okay, if you don't like my water slide analogy, I did my bully example. This is one child has 120 jelly beans. Okay, there's only one bully to get through in that hallway. To speed up how fast you can get through, you give all 120 joules to the bully. You don't need to go through multiple bullies. These are multiple different hallways. So you got to go back to mom, pick up another 120 joules, and then you can go through again. Okay? Yes?
If it uses up all its energy, why does it want to move back to the battery?
So I think this is a little bit to Rihanna's question. And again, it comes down to you're trying to... Why does the ground have 0 joules of energy? Okay? Does that mean it's not moving along it?
Does it mean it's what?
This has 0 joules of energy, yes?
Yeah.
How is it moving if it keeps staying at 0 joules of energy?
Because you kicked it.
So something gave it an umph to begin with and it just kept going that way?
Okay. Wait, so then after the coulomb's charged and it goes through a resistor, it's neutral, and then it goes back and then it gets more energy and it goes.
No, it's not quite entirely perfect. For our analogy, yes. In truth, the charge that goes through there does not go back through. Okay? Each charge coming out. Basically, what you can think of is this. What is actually happening with a circuit is... What is really happening here?
The Coulomb is charged, and then it goes to the resistor, and then it uses the energy.
I think you're going two steps too deep here. So what's actually, we got negatives, right? What are negatives doing?
They're
Repelling other negatives. And so there's a current going in this particular direction.
Yeah.
Yes? Okay. What happens is as those negatives go through here, it takes oomph to get through here, energy comes out, blah, blah, blah. Do the negatives actually go back through? No, 100% they do not go back through.
Where do they go?
They stack right over here. And actually, this speaks to why a battery dies. Why does a battery die? Well, technically, it sort of doesn't. What happens is these negatives keep trying to push through. But what's the problem with putting all of these negatives on this side?
It's full.
Not quite. It's never going to. Not to be underestimated how small electrons are.
The force.
But you are
of
going to
the
stack up like a
electrons,
layer of negatives. What are these negatives going to do to the negatives coming in?
They're going to repel it.
They're going to repel.
The electrons are gonna
So it's going to be hard. So eventually you're going to build it up. And if you haven't ever seen this, this is why you can take a battery. Let's say, I don't know, you're in the last few minutes of Call of Duty match and you got your controller and it seems to, it's been flashing at you for a while, but you didn't want to go get new batteries. So you're freaking out, and then your controller dies. So you take that, you have to learn this skill very quickly. You got to practice on the sideline. You take it, you pop those batteries out, you take them in your hand, wiggle them around, moving the negatives around, making more empty spaces, pop it back in, and it'll work for another 2 or 3 minutes, at least to get you to the end of the match. Why? Because you've moved those negatives around such that you made enough empty holes to possibly do that. Now, you can only do that, I think, based on personal experience, about 4 to 5 times. Before, nope, you're probably not going to make any more extra holes in that particular thing, and you're done. Now, the difference is, do you have a rechargeable battery or an irreversible chargeable battery? The difference here comes from basically here's a here's a normal circuit. Okay, if I want a rechargeable battery, what I then do is I take this battery and I put it in this circuit. Oops, nope. Okay. Guess what this is?
Another thing.
The outlet, 120 volts. You put one of those things, you stick that controller on the outlet, and what does it do? It basically takes the negatives that we're stacking here, pushes them back up the hill, pushes them back where they need to go. Now the issue comes down to how a battery is made, because basically here's the issue. I told you that the way batteries work is they lose ions, yes? In a reversible process, basically take those arrows and instead of coming off, the ions just get put right back on because it's reversible. And now they're not quite as good a little bit later on, but it'll work. You can put them back the opposite direction. The issue is this. If you try to take just any old battery and put them in there, and they are not reversible, then it will not put those ions back. And now you have a crap ton of extra energy not being used to put on those ions back in the opposite direction. And at bare minimum, you have a liquid in a very confined gas with a bunch of extra energy in that system. Guess where extra energy goes? Thermal. And guess what thermal does if you have an encapsulated liquid of any particular type heating up? Eventually, especially if the case is really darn good at holding that pressure in, when it finally gets to a spot where it can actually let that pressure out, you've got a bomb on your hand, which is why batteries that are irreversible, there are so many warnings, do not plug these in chargers because they will explode from all the energy you're basically, but simplistically put, instead of the negatives running this way, rechargeable batteries run them back up the hill to the other side. So ultimately they don't go in a full circle. Okay, the best way to think of 12 joules is that every coulomb has about 12 joules of energy that it can use and will use to go to the other side of the battery. If you want to ask why, that's kind of like asking, why do you use all of the energy of the slide when you go down the slide? I start off at 120 joules. Why do I have to use all of it to go to the bottom? You do. What do you mean, why? I don't know why either. I mean, just as much as I don't know why two positives repel. I don't know why. They do. That's how it works. All right. Let's finish the rules and get back to some problems to work through here. Okay. So we know that voltages are all the same and currents have to sort of split up. Just like in the previous one, it's the exact opposite. The voltages split up and the currents were the same. But while these rules appear almost identical, again, I want to highlight that they are inside different. Here are the main ways. This voltage is not going to get any bigger. It's only going to take the total voltage and split it up, where this current is not splitting up the total current. It's actually adding current in that particular case. The current in this particular case is equal due to the fact that every single location cannot go past the charges in front of it. So if I look at any particular spot, it would be like filling these hallways with every student of the school. Pick any spot along the single path of everybody going around, and you're going to get the same amount of children per second passing by. And if that, say, started at a particular spot, like let's say we started them all down at the office, you would expect just as many kids are going from leaving the office as are going into the office a little bit later on. The easiest way to look at this is basically just this. You've got one path. Can people go faster down one part of the path than the other? No. Same amount of charges per second. Now, why are voltages the same here? Because all of the energy is going to be used going from the top of the slide to the bottom of the slide, no matter which slide you decide to take.
What's the point of having resistors in series when you can just have one big resistor?
So the rules of series and parallel come down eventually to this. We want to control how much energy is out. Yes? But the issue, we sort of can. Basically, we want to control how much energy comes by a particular spot. So let me give you a very basic circuit that I think hopefully explains this circumstance. Okay, here is the basic circuit. That is a variable resistor. Now you saw in a lab how you could make a variable resistor out of a piece of wire. You just change the length that you're going through that wire and it changes it. What you're looking at right now is a dimmer that you have in potentially in your in your living room or wherever. So what do you do when you want the lights to be dimmer? Well, what you do is you take that dimmer and you rotate it. Now what you're actually doing is you're changing the length of the resistor that's in there, and as this resistance goes up, what happens to the voltage it uses? It increases. What happens to that voltage? It decreases, because it's splitting up the total voltage of 120 coming out of the outlet. So, and what happens to current? No, it's going to be the same in both of those, but the total current is going to decrease, because I'm not changing the resistance of this, and the resistance of this is going up. So what's happening to resistance total? It's going up. So what's the total current doing? Decreasing. Now you're right in that total current is the same here and here and here, but the total current is decreasing. So what does that mean about the energy that this light bulb puts out? Less. If I put a resistance in here to double the resistance of that would make that go down by roughly 1/2 and make that go down by 1/2. So the energy we get out is actually 1/4 of what it previously was. And that's why you can turn that up and the lights will go down very, very quickly in terms of how much energy they're putting out. So the answer to your question is that sometimes it can be easier. Your options are to change the voltage. I could put it in series, or I could change the battery or the outlet source itself. And if you're inside of a building like this, are you going to be able to change the outlet source very easily? You can. They're called transformers, but they're a pretty decent size, and you're going to need a pretty considerable power regular.
Aren't they expensive?
No, transformers are like the box on your iPhone. You can pick one up for like $2-3. It depends on what it's trying to do. All right. So here we go. What's happening to the total resistance here? Well, actually, let's go back. What happened to total current given what we said? Increased. Have I actually changed the total voltage? No. So resistance is equal to voltage over current. Okay. This is again where it's sort of confusing. If I look at the totals, what is the total current doing? Increasing, and therefore the total resistance is Now, that is a bit of a misnomer due to the fact that are any of these resistances actually getting less? No. Therefore, are any of them putting out a different amount of current than they usually do? No. But we say that the total resistance decreases because the total current is increasing. This is where it comes back to understanding that resistance is a ratio of blah, 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 blah. All right, now, if I come back to a set of rules that I did the other day, let's switch colors here real quick, and then I'm almost done. And it's this: resistance is equal to voltage over current, so current is equal to voltage over resistance. Basic algebra, everybody cool? Cool beans, let's move on. So if I take that and replace them, then that would be the voltage total over the resistance total is equal to the voltage of 1 over the resistance of 1, and blah, 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 voltage of 2, resistance of 2, plus voltage of 3, resistance of 3, and so on and so forth forever, and the voltages are the same, so they cancel, giving us the rule again, but this time for parallel, that 1 over resistance equivalent is equal to these ratios. And you guys saw this in capacitors. My personal preference, because I think it helps you remember this a little bit better, not on this side, is instead to write it like this. Req is equal to that whole mess to the negative first. Now, that means, simply put, if I have two 100 ohm resistors, then I would go 1 over 100 plus 1 over 100, and what would I get? 2 over 100, but then I would invert them to get. So watch this, because I think it's particularly helpful. Instead of saying 100, this only works with resistors the same size, but you will get a handful of them. Assume they are all the exact same size. What happens when I add all those up? So then I would invert it. So if you have the same resistor in parallel, say it's 120 on all of them, what you can quickly do is figure out, rather than using this method, you can go, that's 40. Just 120 divided by 3, because there's 3 resistors. Does that make sense? Or, what is the total equivalent resistance of that? 60. This time, you got this. 24. All right. Let's move on.
Are we gonna do open ones?
This will be 120. This will be 40. This will be 60, and this will be 100. Our goal right now is to figure out what is the current and voltage of every single resistor in here. Now, let me ask you an important question that's good to see here. How many voltage drops will be in this system? 2. Now, sometimes that answer, by the way, I'll give you another circuit that we're going to do in just a second. If I had said this, how many voltage drops are in that circuit? No. 1 or 2 is the correct way to say that. Now, if you struggle with what we just did, use the chutes and ladders technique, meaning imagine that you are on this path. Here's you, starting at the very beginning. Now, you could go that way, in which case you have 2 slides stacked. How many voltage drops are there going to be that way? 2. And you come back all the way to the beginning. Versus you could have also just gone this way, in which case it's 1. Now, that knowledge alone kind of gets you to like, oh crap, there's only 1 voltage drop here. So what does it have to be? 12 volts. Yes? All right. But here, we don't necessarily know that. Okay, there's going to be 2 either way. So here's what we do. In any one of these circuits, the general steps are always the same and practically identical to capacitors. I told you at the beginning of this that the main goal is usually to find current and voltage, because if you know current and voltage, you know power. You can control how much energy is going where. That's kind of the whole purpose of circuit analysis, showing how much current and how much voltage is going through. So what do? We find equivalent resistors. Which resistors should we combine together first?
You should combine those.
The 40 and the 60. Yes? because they are actually in parallel. This is not in series with either one of them individually. You could argue that it's in series with the entire thing. So find the equivalent resistor of that for me first. And after you find the equivalent resistor, redraw. So it should be 1 over 40, 1 over 60, so 3 over 120, 2 over 120, 120 over 5, right? So that should be 24. Am I right or wrong? 24? Let's make our lives a little bit easier here. I'm going to go back and retcon this. 24, instead of 100, we'll call that 36. Trust me, long term, it's easier. I'm not doing it to be a butt. I'm doing it to make your life easier. Now, they're in series, so what do you do here? Add them. And what do you get? 60. Okay. The next thing that you're going to do is you're always going to find the total current leaving the battery. The reason you can do that is because you have the total voltage and you have what is now the total resistance. Yes? So current is equal to voltage over resistance. So it's going to be 120 volts divided by 60. So what's the total current leaving the battery?
120 divided by 60.
2 amps. And here's what you do now. You work your way backwards just like we did with capacitors. The goal being an equivalent resistor such as this one right here has the same total voltage and the same total current through it as what it represents. So if I look at these two, okay, they have in total, let me have your eyes real quick. I know you guys are working, I appreciate that, and I'll give you some space in just a second. From here to here, what's the total voltage? From there to there, what's the total voltage? 120. Same thing there. Okay? What's true of the current throughout all of these? It's equal. And how much is that? 2 amps. So if you know there's 2 amps in both of those, and you know the resistances, what can you find out about both of them? You can find the voltage, aka voltage is equal to I times R. So the voltage in the 36 is equal to 2 amps times 36 ohms, or 72 volts. And the voltage in the 24 is equal to 2 amps times 24 ohms, aka 48, and you can check to see whether or not you're right, because 72 plus 48 is 120. Now, what you're going to see me do a lot here, I haven't done it yet, but we're going to see a circuit in just a minute. You're going to get to it today? Yeah, we're going to get to it today. In which you're going to get a ton of different resistors and where this really becomes important. So I'm going to start labeling them. You see how I can label them as just 36 and 24, but that doesn't always work. So I'm just going to use letters instead. Okay, I'm going to call that A, B, and C. Then when you start combining them together, this is still resistor C, but this is resistor AB. Then I'm going to come over here on the side because organization is going to make your life a lot easier here. Please make sure you're paying attention to this. Here's the chart that you always want to create. The chart that you want to create also gives you a good idea of the order that you should do this in. First, always find resistance total, followed by resistance total, find current total. Then, I'm going to make a chart out of voltage A, current A, voltage B, current B, voltage C, current C. The nice thing about this chart is if at any point in time you know one of the numbers on the left or right, you know, because of resistance, being a ratio between voltage and current, you automatically, through Ohm's law, know the other one. Does that make sense? Mm-hmm. So, working our way back to, if I had started this way, I know that the total resistance is 60. I know that the current is 2 amps. Then, when I step back to this guy, I can see that resistor C has a current of 2 amps. Now, I didn't put 2 amps up here due to the fact that AB is a combination. But the moment I know this, through Ohm's law, I know the voltage. So resistor C's voltage is 72 volts. Once you're here and you know the current and current and voltage for both of these, current in both is 2, voltage here is 72, voltage there is 48. Once I know everything, I take a step back again. I don't need to worry about that because I already have the numbers over on the side. But now I look at this and I ask, okay, so here the numbers were, voltage was, oops, almost did it poorly, 48. And current was 2 amps. Which of those two is going to be identical for both of these? Voltage. Since it's in parallel, they go to any of this one, they're going to get 48 either way. So I can come over here and say the voltage across A is 48. The voltage across B is also 48. And to get current, if I know the left one, Ohm's law. The voltage of A is equal to the current of A, voltage of A over resistance of A, or 48 volts divided by 40 ohms.
That is so smart to create.
I've done it once or twice.
That's so helpful.
Yet a bunch of you were attempting to fall asleep on me. It hurts. It hurts, dude. 48 divided by 40. That would mean that this current here is 1.2 amps. 48 divided by 60 is equal to 0.8. Now, this is where my people that like to skip steps go, it's Spainhour. I knew that was 1.2. Could I just go ahead and assume it's 0.8 because it has to be the leftover? The answer is arguably yes. My strong suggestion in circuit analysis, because small mistakes snowball very quickly, is don't do that. Just do both steps, because if you do both steps, you automatically have a check for whether or not you're doing it perfectly or not. I have made enough mistakes on circuit analysis to tell you, trust me, take the extra half a second it takes to do the work. And you know you're done the moment you have this. Everything here is filled out. The other nice thing about this is, watch this. Let's replace all those resistors with the exact same light bulbs that have the same resistance. All of those numbers are the same. I then say to you something like, hey, how much power is resistor C getting out? Well, what's power equal to? IV. So the power of resistor C is 148 watts. Voltage times current.
Why didn't you show this to us while we were doing capacitors?
I was booking it through capacitors as quickly as I possibly could so that I could get it done and on the other side, and we've got circuit analysis out the wazoo and like 2 or 3 extra steps beyond this.
Okay.
You gotta trust me a little. I mean, I hear you. Skepticism is important. I get some of you falling asleep at the beginning of the hour, but if Spainhour's up here talking nonstop about something and you're like, this seems redundant and pointless, please remember, he's done this 17 times at least. So there's maybe a reason. Please give me that. All right, questions, concerns on this stuff, or we're going to go to the next one? Cool, let's move on to the next one. All right, let's go. Let's go 20, and then let's go. I did. I'm so sorry. I was trying to say it loud enough. Now, here's another very important thing that I want to say up here. Okay, even actually before you get the numbers here. So let's just go to the aside real quick here. We'll grab this. Actually, we'll copy it. Paste. Let's say you don't have numbers at all. But I say something to this particular effect. This is resistor A. this is resistor B, and this is resistor C. Okay? And I say something to the effect of resistor A is bigger than resistor B is bigger than resistor C. This is absolutely a multiple choice type question right now. Discuss quickly in your group, rank the currents in them from greatest to smallest, okay? And the voltages of each of them from greatest to smallest. You should be able to, and some of them are going to be equal. So it could be such and such is greater than such and such is greater than such and such, or such and such is equal. So see what you got here. So discuss rank the currents and voltages in this circumstance right here. Ooh, did I want? Oh, I wanted this backwards. I'm sorry. I'm changing it again.
Wait, how do we know if the?
Well, that's kind of what you want to discuss in your group. Resistance C is the biggest.
Okay.
Sorry, resistance C is the biggest. I just mixed it up. I need to use the restroom.
What?
So it would be C. Wait, we're supposed to find voltage and what else? Voltage and current. Okay. So the current would have to split. So the current you get more when you go in the parallel. So then the current should.
Yeah, voltage C has
So
to be
we're getting more we're adding resistance with the same amount of voltage on each one. Then that goes through.
I think
The current should be washed.
In the series, in the series,
The current should be
if the sum
larger.
of B and A was greater than C, then they should have
is the highest, has the highest resistance.
yeah, it's less than
Oh wait, okay, sorry, I'm not thinking about the resistance.
Shouldn't split the voltage on
series.
so because the total resistance of top is R,
and the resistance of B
higher.
is
So
Three
can't be certain.
But
That's
then
right.
that means the voltage is greatest than B would be BC. Okay, A and B have less voltage. So that's why I'm going with.
So you're trying to find current C and B. Almost, I guess we have like the actual values.
right?
We don't know. Yeah, the current has to be the same.
Resistance?
Yeah.
And if A plus B, if A plus B is more than C, then they should have less current. If it's less than C.
I got for voltage it goes.
I feel like
C
I can do the math for it, but like my brain is not working. Like I can do the math, I just my brain.
Well, A and B are equal.
Yeah, otherwise you can't serve B.
Wait, if you know C is the greatest resistor, and it has the greatest jelly to what if they all equal?
This chapter is easy. They don't have C and R plus B. Like the current with top and current bottom B different.
What do you mean? Current of A and B are the same.
Yeah, but C.
See, well, that's the thing. It depends on how resistant.
That's what I'm saying.
I kind of like
Not
electricity.
35.
I kind of like electricity because we know equal resistance.
Oh, yeah, you're
resistance A plus resistance is equal and greater.
Yeah.
You're right.
Go ahead and use
Yeah. I'm not gonna die probably.
that. I mean, you will.
He's a. Oh.
But
I got you.
earlier.
Oh no.
That's what? Ace?
Oh,
Okay, which one has the greatest voltage? C. Absolutely. Followed by? B, followed by? A. Correct. When it comes to those, it's more important. So some people get really into the looking at simply resistances. If you did that, it actually does work out here. That does go biggest to smallest, but be careful because that's not always how it works. Thank you so much. Okay, I'll give you another example in just a minute where it's exact opposite of that. Okay, why does resistor C have the most voltage? Because that's all of it. Because all of the voltage has to go down that particular spot. Even if resistor C had been the smallest, it still would have the most voltage because all of it has to go through that guy right there. Does that make sense? Had resistor C been the smallest, that would have been the greatest voltage. If it had been the exact opposite, if A was the biggest, that would have been the greatest, followed by A, followed by B. Okay? Now, which one should have the most current? This does kind of matter how much the numbers are in this particular case, to be fair. But more than, well, actually, let's just go back to our numbers so that I can do it. In this particular example, which one should have the most current?
Or no, B had the most current, which is greater than C.
This one would have the most current.
I mean, no, C.
Why?
Then at least it's C.
Because that path has a total of 60. This path has a total of 20. That has the most current. What's going to be true about both of these currents, despite the fact they're different resistances? Since they are in series, they would be exactly the same. 100%. All right, go ahead and do this one now. Find out how much voltage and how much current is in every resistor. Yes.
Why did they pick resistance instead of like conductivity?
Why did they pick the word resistance instead of their...
Why did they pick to not measure the inverse so everything would... Like, it would
So you got to go back, I think, to looking at history of how we understood these things, not what makes the most logical sense. It speaks to, like, it goes back to understanding why the heck we still use the words EMF despite the fact it's not a force. Why do we use EMF despite the fact that it's actually a voltage? Because it was so prolific in the understanding that to call it EMF, that once they finally figured out it was voltage, slowly over time, it was like, no, that's just a voltage. It was so ingrained. It's the same reason, like I said before, why we use miles and feet and yards in spite of the fact that it's stupidity compared to meters and kilometers. Type of thing. I will say this about it, though. People talk about, English units being stupid because they're random. But here's the truth of it. Because they are random, it is easier to memorize the differences than if it's 1,000. And it's usually, I would argue, easier to spot when things should get bigger or smaller for people that don't understand it very well. All right, so I'll do the first couple parts that you should have already done. The first thing that you should do is this. If you don't follow my why I did this, then this is the first thing we need to discuss. Oops, no, not that. I wouldn't do that. $15, right?
Yep. Oh wait, what was the voltage? My bad. I didn't see it.
12.
Okay. Thank you.
So you should have, if you did this correctly, you should have these things. Resistance total is 15. Current total is 0.8 amps. Yes?
Mm-hmm.
Is that a yes, or do you want to address certain things? Oh,
We needed a few minutes.
come on, that was super.
But yeah,
You got this.
We got it.
Time. Be faster.
We're trying to
Now.
understand it. We see how it is.
Get on my level.
No, I was actually doing it. No, Spinner, are you being so proud of me? I started the homework yesterday, and I did it, and I got every single one of them right, like the first try. I was so happy.
What was the question? What was the question you were just asking me about them?
It was how, because I didn't understand, like, how the voltage split, because the homework, like, they showed
Do you understand it now that we talked about it
Yeah,
further?
because you multiplied it. You said that the current was the same on both sides, so you multiplied. You took the thing and you multiplied by the resistance on each side.
Can you tell me the number?
It wasn't really. I don't know. I think it was just all of them, but maybe like 2. Yeah, 2. Here, come here. I have my work if you want to see it.
I don't. We're good.
No, but like
Okay,
just the way they
so
showed it.
this right here.
Yeah.
Oh, this also brings up an excellent point, by the way, on how they design circuits and how it's kind of confusing. All right, so we talk a ton about potential difference, okay? Basically, what they're doing here is they're saying there's a potential difference between these two, probably caused by a battery. One thing we don't always get to, though, that's going to become important a little bit later is that there are actual potentials going on here. Meaning, most people, when looking at this, are probably going to say something to effect of, this is, this, what is the voltage they have? Oh, they don't even tell you. But this guy's 120 and that's 0. But also, it could be that this potential here is 130 and that's 10. Okay? The difference between potential, actually, I'll show it after we're done here. I can show it on this probably a little bit better anyway. So, what do you know what's the same and in series? Sorry, what's the same in parallel here as this one?
Voltage.
So you know the total voltage is 12, so each of these is getting 12, yes? So the current in the 60, switching colors, the current in the 60 is going to be 12 volts divided by 60. The current in the 20 is going to be 12 volts divided by 20, so that should be 0.6 amps, and if I'm not mistaken, that is 0.2 amps, and that makes sense because 0.2 plus 0.6 gives you 0.8 right there. Then you split it up further. We know the total voltage and the total current in both of them, so going back, I know the total voltage is 12 here and the total current is 0.6. Up here, what stays the same and what splits? Current's the same, voltage splits. So with current being the same, I can use that and say that, hey, I know the current in both of them is 0.2 amps. So the voltage in the 15 is going to be 0.2 amps times 15. And the voltage in the 45 is going to be 0.2 amps times 45. Therefore, let's see, 2 times 15 is 30. Point that, so it's 3 volts. And this is 0.2 times 45, so 90, add the decimal, 9 volts, which makes sense because 3 plus 9 is 12. Now, what I was mentioning a second ago is the difference between potential difference and voltages. Meaning, here's how you can kind of think about it. This charge right here is 0 volts, or 0 joules per coulomb. This charge here, 12 joules per coulomb. Now, obviously, as you step down through this guy, we said it uses all 12 volts. So what would the potential be here? 0. It changed by 12 from 12 to 0. Yes? But if it went this way, it would have 12. What would its potential be after this resistor? What's the potential difference of the 15 ohm resistor? 3. So it starts with 12, which would mean its potential here is 9. Does that make sense? So that becomes important when you start trying to take sections of the circuit and compare them to other things, which you'll see a little bit later on. So the potential here is 12 volts. It lost 3 to 9 volts. It lost 9. Obviously, it should always work out to end up here at 0 volts at the very bottom. Okay? And had I tried to say something like, hey, that's not 0, it's 2. Well, that would make this guy 14 because the difference has to be 12, right? And if it starts at 14, after going down by 3, it would be at 11. And after going down by 9, it would be at 2. 2. And this guy starts at 14 and goes down by 12. So it has to end at 2. All right, let me give you a problem that I gave AP1 students for the longest time while doing this particular content in that class. And this is where we will end today because I'm gonna guess you're gonna need the whole time.
Oh, 11 minutes?
Maybe more.
Oh.
You're scaring me.
Where's it at? Complex circuits. Yeah, I used to give it to AB1. 100%.
It can't be that.
Did you
that bad.
teach circuits in AP1?
Yes, for a long time. It used to be on the test too, but they've changed things over the years. Okay, that one's too easy. So that one right there. To be fair to you on that one, I do not ask them to find both current and voltage in every resistor. If I gave you something like that, two things. One, this question literally says find the total resistance. That's all that one says. Find the total resistance. Number two, what I could do with a problem that big that some of your homework might do is instead of saying, hey, find the current and voltage in every possible resistor, it would say find the current and voltage of that one. Now, still a decent amount of work. You'd still start off the same way, but rather than worry about absolutely everything, you're just going to focus on everything having to do with that particular resistor. Okay. But this is a circuit that we do regularly do. Okay, I want to talk about this because it happens all the time. So let me share with you how this just says find the total resistance of this guy. And here's what students do, okay, versus what they should do. They go, okay, so it's 1 over 3 plus 1 over 9, and I'm going to invert that, and I'm going to get an answer. And then 1 over that answer plus 1 over 1, I'm going to invert that, and I'm going to get an answer. And then that answer, 1 over that plus 1 over 7, and they do that. Except that's a lot of work. When are these all just separate paths? Yeah, I could go this way. Or I could go this way. Is there one resistor down each? So are all of those in parallel with each other? Yes. The way I'm doing that is 1 over 2 plus 1 over 4 plus 1 over 7 plus 1 over 1 plus 1 over 3 plus 1 over 9, then inverting it. Now, if I don't ask you to do it such quite quantitatively, I should be able to ask you this. I'm going to put a number here, and you tell me whether or not it's possible. Okay? The total equivalent resistance of this is 1.5. Yes or no? You should be able to quickly figure that out.
No.
Why not?
Because it would have to be less than the least.
That's what I was looking for. Yes. The smallest resistor is 1, and therefore you know that the total equivalent resistance has to be less than the smallest, just the same way as in series it has to be greater than the greatest. So it would definitely be less than 1. All right, but finally let's get to which one? Yeah, let's do that one.
Did you make that?
Yep.
Yeah, I could tell. Can you not tell it's individual?
Yeah, I know. I can tell. I can definitely tell.
That's my favorite.
I don't like. No, that one's 2 something. I don't know what it's 2, but it's 2.
We're
Let's
bursting
just talk about, yeah.
Come on, Spinner, hurry up.
Too easy.
I heard these are pretty tough.
Oh wait, no, don't do the open circuit.
That one. No. Where's something else? No.
It's looking for a specific one that he knows that.
Yeah.
Yeah.
He wants us to like.
You know what? We have the perfect amount of time for another one. Yeah.
Oh.
Wait, so are we not learning open circuits today?
What do you mean learning? We already know about open circuit.
Not the open circuit, but like the one, like on the homework they have the one where it's like the little line that's. Can we do one of those? I was confused. Yeah, that thing.
Which light bulb is on?
The bottom one?
The bottom.
Okay.
Let's go to the top one.
You close the circuit. Which light bulb is on?
Oh.
What happened to the bottom light bulb?
It got less.
It stayed the same.
Nothing's great. Why did it stay the same?
Oh,
Because
because.
they're parallel.
But then if they're in series, then they get different. Because the voltage is not gonna.
It just drains the battery faster.
Which light bulb is on?
Both of them.
Neither. We need it neither.
Wait, what? Oh, I didn't see that.
Let's do this.
Good. I'm a big fan.
Which light bulb was on?
Neither.
Okay. I close this switch.
The first one's
Just
on.
the
First one's on.
No? No?
Wait.
What?
Two truths make a
Short circuit.
Wait.
Remember that?
Just why? Why?
That's correct. Just the first one.
Because it runs through the.
Oh, it just runs. Yeah.
Is there any reason for charge to go through the other path?
No.
No. It could just go straight back to the battery.
What's the point of the other one then?
That's the point.
It's a red herring.
There's no point if
Let's
it's
go
not
to
much
this.
Right.
Okay.
Now that one's open. So
No. Okay. So this was once again. Which one's on?
the first one.
First one. Okay.
But when you open that, the second one will go on.
Now which one's on?
No.
Which one? What happened to the first one?
You got dimmer.
Why?
Because
they're
it's in
series.
series.
There are
The
two
voltage is
reasons.
split.
That's one of
The
them.
voltage has to split. The
And
current.
she's right. The voltage split. So this battery just got less voltage than the total. But there is a second reason why it got dimmer.
Current decrease?
Current also decreased. Both of those, but keep in mind, in my dumb analogies, we go back to the kids on the hill. Okay? In this case, I made the hill half as big, but I also have half as many kids going down it. So actually the power of that hill reduced by 4. Does that make sense-ish?
Yes.
Okay.
It was because current decreases too, because if the voltage is splitting, then the current has to be.
What happens as like a circuit like approaches its maximum current from like
It always pushes, it does that very quickly.
adding too many resistors in like parallel?
Oh, excellent question.
Is it
Okay,
just
so you know the
equal?
answer to this, but it's a good thing to connect it. What does happen?
Maybe we can do it as a bell ringer tomorrow.
No, we'll start today and then we'll do it into tomorrow.
Okay.
Gabe, how much current is in your toaster? How much current is in your toaster?
2,000 amps.
Seems like a good one.
That's my bread on fire.
Jaden.
When is the mousetrap car actually due?
2 weeks
split
after.
the cost
Okay.
between like a we split the cost.
Hi, Ava.
Dude, you just
What if we just made it yacht?
no, Gabe.
Like had a ditty party.
Gabe, what if you okay? What if you, me, and Jaden split the cost between like a retired, like what's it called? A retired like fighter jet, and we use jet propulsion on our boat, and we fly away.
We're not allowed to use.
You're not.
Have you guys
Unless
started
you
your
design it
boat?
out of cardboard.
Yeah.
Freaking A, we found it. Out here it is.
No.
7 minutes.
We got this.
7 minutes of work done.
We're gonna be speedy quick.
I like to take my time. Didn't Jaden ask a good question?
Sure. What is it?
I don't know. Jaden.
Oh, the
The
maximum.
The more resistors you have in parallel, it means like the current has to go up. But isn't there like a limit to how far up it can go?
What the
I
heck?
only deal with boxes.
Good news for you then. You can change into the A box. So that is one of the reasons I draw these pictures this particular way, is because you can always feel free to rewrite circuits, especially when we get to kind of a real circuit that are
That's
floppy and
what
all
I'm
over the place. You definitely want to. Here's the rule. You can always redraw it in a square as long as you don't change the order of the wires. Okay, you can move a wire along another wire perfectly. So like in the analogy, like this one, if I had, say for example, something and I was like, ooh, hey, Foopy over here, and then this one is Foopy in here, and then we've got another Foopy going this way and coming back down. Let me show you how I would redraw this. Number one, I'm gonna move this guy. I'm gonna watch here, trust me. Move this guy so they all intersect at the exact same location. Okay? That doesn't change anything whatsoever. Number two, obviously if you want it to be a box, that's completely fine. you go. So it takes a little bit of practice doing that. Please feel free to do that here. Now, the size of the resistors are going to be as follows. Let's go 60, 140, 200, 400, 100, 100, and 150. Now, so that we all agree about what to call these and we're on the same page, usually if you just got something like this, it's probably going to already have them labeled so that we don't disagree, or it's going to have different numbers for all of them, so we can say the 60 ohm resistor, blah, blah, blah. But for our purposes right now, I'm going to label them so we all agree here. I'm going to call this guy, let's just go in, I'll go clockwise.
Oh my gosh, I just labeled them all.
B, C, D, E,
okay, good.
F,
We're good.
and G.
Darn it.
I labeled mine right.
And the question is, what is the current and voltage in every single resistor? Now let me ask you this before we get going too hard. How many voltage drops?
1, 2, 3, 4, 5. Oh wait. They're the same there.
3.
So 1, 2.
Or there's another option. It's 3. 3 could be one of them.
Not 3.
So here you go. I got you. If I'm passing, it'd be 1, 2, and either one of those would be 3.
3 or 4.
Yes, the answer is 3 or 4. So are any resistors up there getting all 120 volts? Absolutely not. Yes.
On the first the diagram you're doing straight behind you.
Yes.
Like when it connects to the other one, how can you say that they all meet at the same exact point?
Current and
Fast,
voltage
on
of
down,
every single.
So again, current wires don't have resistance, so they don't really affect things whatsoever. What would actually happen is, let's assume, for example, in this particular case, it had been the case that all of them are going to have the same current. Okay, so like when I was here, if I said there's going to be the same current in every path, truthfully what would happen is that would have the amount, that would have the amount, and that would have the amount. This section right here would have twice that amount. But as it has no resistance, it doesn't change the voltage in the slightest. And so to say that this is going here does not change the current in each resistor, which is what we're looking at. What is the current in each resistor? Since the wires basically have 0 resistance, you can move them around as long as you don't change the order. So again, the easy way to say it is you can move a wire easily along a wire. At the moment you move a wire on the other side of a resistor, now you've made a different circuit, which is going to mess things up.
C is 200, right? I'm just making sure I see that.
C is 200, yes. It goes A is 60, B is 240, C is 200, 400, 100, 150, and 100. I'll give you a couple of answers to get started with here. Let's see, that should be... That whole section there is 80. If you struggle with that section, here's how you could redraw it. You could redraw it like this. Is that easier to see it that way?
Yeah.
Completely fine, but just know that I'm not always going to give circuits like that, so you need to kind of practice the transition between those two. So that's 80, that's obviously 100. That's 60. So the total, I forgot about this. The total resistance is just 240.
Stop spoiling the answers.
Maybe.
I'm still finding it out. I just got the answer.
The total current is a half. Which one of these resistors, see if you can do this quickly, which one of these resistors have the most current in it?
The one with the
Oh.
All of them are
Oh,
equal.
I see what you're saying.
Wait. A and B.
Nope.
F.
Nope.
G.
Nope.
Trick question.
I mean, arguably yes, because all of you are getting it wrong, but not inherently. The answer is E, people.
G.
Because it's the only one that's like.
Where's all the cars have to go through at that spot?
Yeah.
They all got to go through E. They split up on every single other possible resistor. Again, if you look at those as lanes of traffic, it becomes easier to spot where total current should be. Oh, Jaden, to this particular effect.
Is that just when like a battery dies?
We talked about why batteries die.
Like it just like I don't know. Never mind.
So like since you're comparing this to
Jaden, since you asked this the other day, let's see if I can't bring it back up again now with you having a little more understanding.
Don't forget
Do
to
you-
end your recording.
Oh, sure, thank you.
Are you coming to yoga tonight?
I was planning